So, under the general organic chemistry, let us see another feature called resonance. This is also one of the important phenomenon which is also going to govern several the important issues in the organic chemistry. Based on the resonance reason, we are able to sustain why this product is formed, why not that product is formed, and so on. All the discussion, that is basic reasons, are we are deriving from the application of this resonance. However, resonance is there in the general chemical bonding also, having the so many rules and all that, but we are not much concerned about all that rules. Let us be precise with reference to the organic chemistry. How the resonance is coming into the organic chemistry is more now we are important. However, we take elaborate examples in terms of organic chemistry to understand or to see the applications of this resonance. So, let us define the resonance. It is a phenomenon in which the existing a molecule or it can be ion, molecule or ion in more than one structure, It's a small definition only. Actually, the existing a molecule or ion in more than one structure is a small definition, but to understand this particular statement or to apply to the different molecules is slightly ambiguity is there. An example, let us take one example. I have taken a methyl chloride and writing another structure for the methyl chloride. Let me try. So, the bond I will break and makes the CH3 plus and the Cl minus. Is it the another structure for the methyl chloride? Means as per the rules of IUPAC in that the resonance, the sigma bond cutting is not allowed. So, therefore, this is not the right example. Another example let us take. Sigma bond is not allowed, isn't it? So, therefore, I will take one molecule. This pi bond I open, previously sigma bond I opened, now the pi bond I am opening, writing the CH3, CH2 plus and CH2 minus. Is it the method to write a new structure for the molecule? Means again this is also wrong. So, both these two examples are instead of examples, they are non-examples in fact, non-examples for the resonance in fact, because in the resonance only pi bond opening and making back again pi bond formation, this is not the resonance. Then under what condition or what is the requirement or what examples exactly says this resonance means? The requirement for this resonance is, first one is pi conjugation, pi conjugation. So, a pi bond whenever attached with another pi bond in an alternative pattern, that is one pi bond, another pi bond is alternative pattern. This conjugation exact meaning also we are putting that alternative pattern whenever the pi bond, another pi bond is arranged, then this is the one of the eligible condition. Now, this pi bond, 2 electrons will be coming here to make a pi bond. These 2 electrons will go to the carbon. See, they carefully observe the arrows. One arrow started from the pi bond and ended on the sigma bond. That means these 2 electrons are shifted to here. These 2 electrons started from the bond, ended on the corner. That is where from exactly we are starting, ending. You can use a big loop, but where it is started, where it is ended, exactly precisely you have to show. These 2 electrons are shifted. So, consequently what you will get is a CH2, this will become a sigma bond, single bond, and this corner will get a positive charge, and the double bond is shifted to the center, and the other side this pi bond is shifted to the last carbon. So, therefore, you will get a minus charge. Now, this minus again if it is given to this one, the pi bond comes back here, so that the plus is nullified, again you will get back the original. So these two are going on exchanging fastly, and it is a state comes. In fact, there are no two items, there is only one item, either this or that. It can have two different types of the structures. So it is not there are two structures for the given compound. In fact, that is the wrong concept. One molecule can exist either this way or that way, sometimes like this, sometimes like that, right. So this and that totally only represent the properties of the molecule. So this resonance structure is nothing but the same thing. So this compound is called 1,3-butadiene. A comes an extra for the soft pronunciation, otherwise butadiene. Butadiene. What is the name of that? If another name is given according to the IUPAC, that will become another compound, right. So that compound is nothing but the same thing. So you have to write a resonance structure of so and so dash 1,3-butadiene. Specifically, you can say one thing: no charge. There is no charge, isn't it? A neutral structure of butadiene, plus minus charge separated. You can add this charge separated resonance structure of 1,3-butadiene. Same name should be given. You cannot write another name. Now these two compounds are fastly exchanging, and a specific symbol is also allotted instead of the two-side reaction. An arrow having two-side hooks. This is the special symbol used for the resonance. It is nowhere allowed excepting this particular one. These two arrows shows there is an equilibrium, or you can use this type of arrows. This is all equilibrium symbols. That is arrow that side, arrow this side, shows A is becoming into B, B is becoming into A. There are two items are there, A and B. Here it is not like, there is only one item A that can also represented as another structure, but the compound is only one. There are two compounds are going on exchanging the structures. That is different concept. This is totally, this is nothing but that only one of the structure of this compound. So that compound should not be given another name, but you can say charge separated resonance structure of 1,3-butadiene, right. So let us go for another example, another condition. Pi and a pair of electrons, this is called P, pi p conjugation. Here the P stands for a pair of the electrons. A best example is a pi bond for ethylene. Adjacent one atom you take, chlorine. It will have actually three pairs, but one pair is enough for me to show this resonance. So this pair, if it comes here, the double bond goes to the corner, and you will get a resonance structure of this compound. So resonance structure, I am using this specific symbol, double headed arrow, and this compound will get a, now this side minus charge, that side you will get a double bond and the Cl, only two lone pairs, one pair is missing, but a charge, like a plus charge is for. Now this compound has a chloroethene, or we have a common name called vinyl chloride. Vinyl chloride. So how do you call the other compound? That is also once again vinyl chloride only. As I said, you cannot give a new name. At the most here neutral form, that is a charge separated form of the vinyl chloride. Condition here is a pi bond and a lone pair. One of the lone pair is conjugation. So under condition, this condition fulfills. Another third condition is also there. Pi and charge can be conjugation. Pi charge conjugation, third condition is called pi charge conjugation. The charge can be three types. It can be positive, it can be negative, it can be dot also. In fact, dot charge wise, if you say positive, negative, this is neutral, isn't it? Dot is not a plus or minus, neutral. Even dot is allowed as a charge and considered as a resonance structure, you can write. An example, if a CH2, a double bond CH, a CH2 with plus charge, right? Now if this pi bond comes here, there is a double bond exists, this side will become a plus charge. So this side you will get a plus charge, and you have a, that side you will have a double bond. So this is called what? A allyl carbocation. Allyl carbocation. That is called resonance structure of allyl carbocation. Another name cannot be given. At least in these two there is one point. This and that is not same. This and that is not same, isn't it? Here this and that is nothing but same, right side, left side, that's all. Now in the resonance, in this particular example, we have one more problem of understanding. This is nothing but the same thing. How can you say it is another structure? No. Just because of two, let us say one train is gone, another train has come, same type of model is there, we can't say that is the only one train, isn't it? Just because of two trains are identical, you can't say there is only one train. At a time if they come, you can say two trains, but one after the one is coming, all are identical, therefore you can't say there is only one train, isn't it? Like that, their two structures are different, there are two structures are there for the same compound. You can visualize this phenomena. For example, in this CH2, if I have instead of one CH2, one methyl is there, okay, the rest of the structure is same, double bond with the CH and the CH2 is there. Now this key methyl will be there in the next structure, but the double bond, if it is coming here, what happens, you see, this methyl will be intact, but the double plus charge will come this side. Now I only changed, instead of one hydrogen, a methyl is added. This is the part I added, this is the part I added. If this methyl is not there, you are arguing these two are identical. Just because of the methyl, now you are saying this is different then. Because methyl side carbocation, methyl opposite side carbocation. That means just because of this methyl, we now able to recognize these two are different, isn't it? So methyl is same one, isn't it? So therefore these two are inevitably they are different structures, only thing is they are identical. So resonance structure sometimes will have a different structures, sometimes they may be a identical structure may be there. So this type of three conditions, the charge can be plus or minus or dot also, even with minus also you will get an example with the minus I will write here, a CH2 double bond with a CH2 minus. When minus is there, you can't give the electrons to this side, isn't it? Instead, the minus will be given and the pi bond goes to this carbon. So where it is started, where it is ended, you must show very clearly, so that the movement, this arrow, that is a bent arrow, a curved arrow, shows movement of two electrons. So clearly, the structure will become now another allyl carbanion, this side minus will come, that side double bond will come. Allyl carbanion, allyl carbanion. Similarly, a CH2 double bond with CH2, a free radical, one electron. Now resonance writing will be slightly differs in this case. When you have one electron, I cannot bring two electrons and make three electrons to have a bond. So homolytic fission you have to show. One electron coming here, one electron coming here. See that the shift is only one electron. So therefore a curved arrow with one side hook. One side hook shows shift of one electron. So other electron goes to this corner, right, carbon. So therefore you will get this side CH2 will become dot, that side you will get a pi bond. This is also allyl free radical, this is also allyl free radical. So when free radicals are involved, the arrows should be used one electron shift, okay. This minus if it is given, this goes like this. Here a full two side arrows I am using. When one electron is there, only one electron shift I am showing. So therefore there is a difference between this. However, the symbol is same. You can't use half, that is one sided hook arrows. The same symbol resonance I am using. So the three conditions, either with the dot or with the minus or with the plus charge, a pi bond. Inevitably in all these three systems, see, pi should be common. So you can make one statement, without pi bond, resonance cannot come. In all the system, inevitably pi, two pi bonds, or a pi bond with a pair of electrons, pi bond with a charge. When alternatively is there, we are going to establish this type of a structure with more number of structures may be possible. In fact, it is not necessary only two. We have another structure for this particular first example. If the electrons are gone that side, you will get that. Instead, if the electrons are coming this side, you will get this side CH2 will become a minus charge. and that side you will get a positive charge. And again the same argument, what is the difference between these two? Minus and minus, plus and plus. Now let us have, instead of one hydrogen, if I put some group here, okay, the group containing cation, a group containing anion are different. Now these two are not identical. Previously they are identical. Now with the moment group is there, they are not identical. That means this butadiene in fact has got three structures. One is resin, that is without having charge. One is right side negative, left side positive. The other one is right side positive, left side negative. All these three structures are going on, exchanging, and represent the conjugate, that is a resonance structure. So what is the resonance advantage or the result? So all these three types of resonances are there. Eligibility criteria using, we are classifying into pi pi, pi p and pi chi. Now let us go to another aspect. What is the result of the resonance? Result of the resonance. So let us take another aspect of the resonance is a result or benefit of this. What is the outcome or the benefit of this resonance? Whenever resonance comes, the molecule potential energy decreases. How it is decreases? When a molecule, for example, let us say there is another example, a benzene is there, okay. The benzene, what happened? This double bond comes here, this double bond comes here, this double bond comes here. So you get another resonance structure for this benzene is, so double bond will be here and here and here. So whenever a structure 1 changes into structure 2, both are however almost the same type. This is benzene, that is also benzene. Benzene first structure, let us say benzene second structure, both are going on changing the structures. And what is the benefit of going on changing the double bond? Just like a bird sitting on the wall, if somebody want to fire it, if the bird changes the place, we cannot fire it, isn't it? Because a bird, sitting bird, you can fire it, but when it is moving, you cannot. Just like that, if this molecule I am treating with the bromine, the bromonium cation is likely to attack the double bond. Taken grant there is a double bond, it will go and try to attack. By the time the bromine goes there, it will become single bond. That means the attack will become fail. When there is a double bond only, the bromine molecule, each side will attack. So if the double bond becomes single bond, the attack will become waste. Thinking that the bromine, the double bond is here, it will go there, again it will become single bond. Just like that, the bird is escaping from the target by moving the place. Even the double bond also doing the same thing. This is the target is going to attack, but the double bond is changing the position. So whenever the in butadiene or in all the systems, pi bond is changing, isn't it? Pi bond changing means attacking target is escaping, or charge has a problem. So constantly, if one problem is at one particular place is a problem, just like I am carrying one bucket. For a longer time if I carry, I have a pain, but I can transfer this bucket to here. I am not leaving the bucket, but I am changing the place. Just by changing the place, I got some relaxation in this hand carries. Like that I am going on change. So if a minus charge, need not to be addition reaction. Let us say there is a minus charge is there, CH3. This minus charge is a problem. Now if the minus comes here, this goes here and you will get another structure. This acetate anion will have the minus for sometimes this side, sometimes that side. So the problem is going on changing. So two atoms of oxygens, one after the one is changing, just like two hands. Perhaps I have more hands, more exchange will give the more. So like that, the more the resonance structures, more stabilization will be there. That is what in the resonance theory says that an ion or molecule, if it gets more number of structures, more stabilization. Stable means its reactivity is decreasing. Okay. So whenever the resonance is there, the first point you can say reactivity decreases. Reactivity decreasing, isn't it? And its stability increases. Stability will be increasing. Its potential energy will be decreasing. All stable molecules will have a less potential energy, decreasing. So, whenever the potential energy is decreasing, some energy is released. Let us say two atoms join, make a molecule, and the molecule potential energy will be less than the so called added potential energy of the atoms. So, in that system energy is released, it is called bond formation energy. Same energy if you give, the bond opens and you will get a bond dissociation energy is required. Bond energy is released, you have to give to break the bond is called bond dissociation energy, which are nothing but same amount. So, here also whenever the molecule, a no resonance molecule, let us say, it undergoes a resonance, its potential energy decreases. So, certain amount of energy is released. That released energy, you can call it as a resonance energy. So, the definition of this energy is very simple. The energy released when a non-resonance molecule acquires a resonance, energy is released. But it is very difficult to measure it. The reason is when two systems, let us say acid and base is added, 1 mole of acid to added to 1 mole of the base, both are if strong acid, strong base, 1 mole of water formed and 13.7 kilocalories liberated. This is always standard for the per mole, not 1 molecule or 10 molecules. So, per mole, 1 mole of acid and 1 mole of base if it added, you will get 1 mole of water neutralization taking place, 1 mole of salt plus the 13 kilocalories, it is standard value. If one of the molecule is not totally dissociating, it will be less, right. Now, this how much energy released, we can see the T1, T2 difference of the temperature raised or increased amount, that is temperature multiplied by its specific heat, then you will get the kilocalories, or in terms of the energy per mass you can calculate. Now, here similarly the resonance energy cannot be calculated, because whenever you add energy comes T1, T2 you can calculate, but here the resonance, when the molecule acquires resonance you cannot. When the atoms join up, molecule is formed, the moment formed, formation energy will be there. When it is formed, resonance also takes place. So, resonance energy and formation energy will be mixed. So, you cannot identify only the resonance energy. There is only a indirect method to calculate such type of the resonance energy. How to calculate resonance energy means, we have one method, like for example, there is a one butane is there. When you add hydrogen, it gives a butane, right, and plus some energy is released. This energy is called, we are doing hydrogenation, 2 hydrogens are added. This is unsaturated, less stable and more stable. More stable means potential energy decreases. This potential energy, there is a decrease. Therefore, this amount of energy is released. This is called what? Heat of hydrogenation. Heat of hydrogenation. This is also per mole, you say. This is calculated as a 28.6 kilocalories per mole. This is a standard value in the organic chemistry. If one double bond arbitrarily, whether it is ethylene or propene, you can take it grant roughly 28.6 kilocalories per mole, it is liberated. Now, imagine if it is 1 pentene, also makes no much difference, same energy will be released. If 2 double bonds are there, imagine there is a double bond in here and here, and without doing, you can say, oh, 2 double bonds are, therefore it will be the same pentane. Here pentane I have taken, I will get pentane plus some energy. Here also same molecule, how much energy? 2 into E will be formed, that is 2 into 28.6 will be 28 is 56, 57. So, 57.2 kilocalories of heat per mole will be liberated, because 1 double bond that much, 2 double bond, this will be liberated. But it is so happened in one case, when 2 double bonds in alternatively arranged, it is not liberated that much. It gave the again N pentane only, but E will be only 40 kilocalories per mole only liberated. 40 kilocalories only liberated. Why not 57? Means this molecule has resonance. When the molecule is formed, it shows some resonance, some amount of energy already released. Now it is releasing 40. what is the amount of energy at that time released means it is supposed to release 57, only 40 releasing means the difference gap, that is 17.2 kilocalories already released per mole, kilocalories, that is kilocalories per mole already released. That energy is called now resonance energy. Like that, one double bonded cyclohexene 28.6, 3 double bond 3 into 28 is supposed to get, but it gives only 49 kilocalories. That shows 36 kilocalories is less it is liberating. That 36 must be liberated when the benzene undergoes resonance. So therefore resonance energy of the benzene is calculated as the 36. If there is a double bond in the cyclohexene, you get a cyclohexane plus energy, that energy is 28.6, isn't it? So if the 3 double bonds theoretically, you will get the 3 into E, 3 into E must be getting. So this is 3 into E will be not into this 28.6 calculated, but you are getting practically what you are getting only 49.6 kilocalories only. But you should get actually 85 point so something, you must get it, but you are not getting. So the difference of that 3 into this one minus 49, 3 into 28.6 minus 49.6 gives approximately 36 kilocalories. That 36 is called what? A resonance energy of the energy. So resonance energy cannot be calculated directly, it only from the indirectly, because whenever you take molecule, if you say start resonance means it is liberated energy, you can calculate, but whenever the molecule is formed, resonance also is mixed with the formation energy. Therefore an indirect method is suggested for the calculation of the resonance. More the resonance energy, more will be the stabilization. That is, the double bond is moving, so the reagent cannot attack, reactivity is decreasing, stability is increasing, potential energy decreased, some energy is released, that is called the resonance energy. You too can say not only with reference to the double bond addition, but with reference to the negative charge or positive charge. Whenever the negative charge is going on shuffling, the problem is shared by the other points, therefore the stability is coming. The double bond moving the position, therefore the reactivity, that is addition reaction, decreased. Or there is no double bond concept means the charge is delocalizing, therefore it is also stabilization also we are able to explain.